In today's live, we will be reading Chapter 12 Magnetic Effects of Electric Current. This is Chapter 12 taken from NCERT Class 10 Science, which is being followed in the CBSE board. In case you are interested in hearing the audio, then this video will be helpful to you. This is not an explanatory video for Chapter 12 Magnetic Effects of Electric Current, just the audio. Once you are done with this chapter, you can revise by hearing to the audio. In case you are interested in such videos, earlier all the 11 chapters are being recorded and they are uploaded in a playlist with the name Audiobook Class 10 Science. So you can visit the playlist of my channel and you can move ahead. I hope the screen is clear to everybody. So let's begin with the live reading of Chapter 12, Magnetic Effects of Electric Current. In the previous chapter on electricity, we learned about the heating effects of electric current. What could be the other effects of electric current? We know that an electric current carrying wire behaves like a magnet. Let us perform the following activity to reinforce it. Activity 12.1. Take a straight, thick copper wire and place it between the points X and Y in an electric circuit as shown in figure 12.1, this one. The wire XY is kept perpendicular to the plane of the paper. Horizontally, place a small compass near to its copper wire. See the position of its needle. Pass the current through the circuit by inserting the key into the plug. Observe the changes in the position of the compass needle. We see that needle is deflected. What does it mean? It means that electric current through the copper wire has produced a magnetic effect. Thus, we can say that electricity and magnetism are linked to each other. Then, what about the reverse possibility of an electric effect of moving magnets? In this chapter, we will study magnetic fields and such electromagnetic effects. We shall also study about electromagnets, which involve the magnetic effect of electric current. Hans Christian Ørsted, born in 1777 and died in 1851. Hans Christian Ørsted, one of the leading scientists of the 19th century, played a crucial role in understanding electromagnetism. In 1820, he accidentally discovered that a compass needle got deflected when an electric current passed through a metallic wire placed nearby. Through this observation, Ørsted showed that electricity and magnetism were related phenomena. His research later created technologies such as radio, television, and fiber optics. The unit of magnetic field strength is named the Ørsted in his honor. 12.1 Magnetic Field and Field Lines. We are familiar with the fact that a compass needle gets deflected when brought near a bar magnet. A compass needle is in fact a small bar magnet. The ends of the compass needle point approximately towards north and south directions. The end pointing towards north is called north seeking or north pole. The other end that point towards south is called south seeking or south pole. Through various activities, we have observed that like poles repel while unlike poles of magnets attract each other. In text question 1, why does a compass needle get deflected when brought near a bar magnet? Activity 12.2. Fix a sheet of white paper on a drawing board using some adhesive material. Place a bar magnet in the center of it. Sprinkle some iron fillings uniformly around the bar magnet, figure 12.2, this one. A salt sprinkler may be used for this purpose. Now tap the board gently. What do you observe? The iron fillings arrange themselves in a pattern as shown in figure 12.2, this one. Why do the iron fillings arrange in such a pattern? What does this pattern demonstrate? The magnet exerts its influence in the region surrounding it. Therefore, the iron fillings experience a force. The force thus exerted makes iron fillings to arrange in a pattern. The region surrounding a magnet in which the force of the magnet can be detected is said to have magnetic field. The lines along which the iron fillings align themselves represent magnetic field lines. Are there other ways of obtaining magnetic field lines around a bar magnet? Yes, you can yourself draw the field lines of a bar magnet. Activity 12.3. Take a small compass and a bar magnet. Place the magnet on a sheet of white paper fixed on a drawing board using some adhesive material. Mark the boundary of the magnet. Place the compass near the north pole of the magnet. How does it behave? The source pole of the needle point towards the north pole of the magnet. The north pole of the compass is directed away from the north pole of the magnet. Mark the position of two ends of the needle. Now move the needle to a new position such that its south pole occupies the position previously occupied by its north pole. In this way, proceed step by step till you reach the south pole of the magnet as shown in figure 12.3 shown this side. Join the points marked on the paper by a smooth curve. This curve represents a field line. Repeat the above procedure drawn and draw as many lines as you can. You will get a pattern shown in figure 12.4. These lines represent the magnetic field around the magnet. These are known as magnetic field lines. Observe the deflection in the compass needle as you move it along a field line. The deflection increases as the needle is moved towards the poles. Magnetic field is a quantity that has both direction and magnitude. The direction of the magnetic field is taken to be the direction in which a north pole of the compass needle moves inside it. Therefore, it is taken by convention that the field lines emerge from north pole and merge at the south pole. Note the arrows marked on the field lines in figure 12.4. Inside the magnet, the direction of field lines is from its south pole to its north pole. Thus, the magnetic field lines are closed curves. The relative strength of the magnetic field is shown by the degree of closeness of the field lines. The field is stronger, that is, the force acting on the pole of another magnet plays this greater where the field lines are crowded. See figure 12.4. No two field lines are found to cross each other. If they did, it would mean that at the time of intersection, the compass needle would point towards two directions, which is not possible. 12.2 Magnetic field due to a current carrying conductor. In activity 12.1, we have seen that an electric current through a magnetic conductor produces a magnetic field around it. In order to find the direction of the field produced, let us repeat the activity in the following way. Activity 12.4. Take a long straight copper wire, two or three cells of 1.5 volt each, and a plug key. Connect all of them in series as shown in figure 12.5a. Place the straight wire parallel to and over a compass needle. Plug the key in the circuit. Observe the direction of deflection of the north pole of the needle. If the current flows from north to south as shown in figure 12.5a, the north pole of the compass needle would have move towards the east. Replace the cell connections in the circuit as shown in figure 12.5b. This would result in the change of the direction of current through the copper wire, that is from south to north. Observe the change in the direction of deflection of the needle. You will see that now the needle moves in opposite direction, that is towards the west. Figure 12.5b. It means that the direction of magnetic field produced by the electric current is also reversed. 12.2.1 Magnetic field due to a current through a straight conductor. What determines the pattern of the magnetic field generated by a current through a conductor? Does the pattern depend on the shape of the conductor? We shall investigate this with an activity. We shall first consider the pattern of the magnetic field around a straight conductor carrying current. Activity 12.5. Take a battery 12-volt, a variable resistance or a rheostat, an ammeter, a plug key, connecting wires, and a long straight thick copper wire. Insert the thick wire through the center normal to the plane of a rectangular cardboard. Take care that the cardboard is fixed and does not slide up or down. Connect the copper wire vertically between the points X and Y as shown in figure 12.6a. In series with the battery, a plug, and a key. Sprinkle some iron fillings uniformly on the cardboard. You may use a salt sprinkler for this purpose. Keep the variable of the rheostat at a fixed position and note the current through the ammeter. Close the key so that a current flows through the wire. Ensure that the copper wire placed between the points X and Y remains vertically straight. Gently tap the cardboard a few times. Observe the pattern of the iron fillings. You would find that the iron fillings align themselves, showing a pattern of the concentric circles around the copper wire, figure 12.6. What do these concentric circles represent? They represent the magnetic field lines. How can the direction of the magnetic field be found? Place a compass at a point, say P, over a circle. Observe the direction of the needle. The direction of the north pole of the compass needle would give the direction of the field lines produced by the electric current through the straight wire at point P. Show the direction of an arrow. Does the direction of magnetic field lines get reversed if the direction of current through the straight copper wire is reversed? Check it. What happens to the deflection of the compass needle placed at a given point if the current in the copper wire is changed? To see this, vary the current in the wire. We find that the deflection in the needle also changes. In fact, if the current is increased, the deflection also increases. It indicates that the magnitude of the magnetic field produced at a given point increases as the current through the wire increases. What happens to the deflection of the needle if the compass is moved away from the copper wire but the current through the wire remains the same? To see this, now place the compass at a further point from the conducting wire, say at point Q. What change do you observe? We see that the deflection in the needle decreases. Thus, the magnetic field produced by a given current in the conductor decreases as the distance from it increases. From figure 12.6, it can be noticed that the concentric circles representing the magnetic field around a current carrying straight wire become larger and larger as we move away from it. 12.2.2 Right hand thumb rule. A convenient way of finding the direction of magnetic field associated with a current carrying conductor is given in figure 12.7. This one. Imagine that you are holding a current carrying straight conductor in your right hand such that the thumb points towards the direction of the current. Then your fingers will wrap around the conductor in the direction of the field lines of the magnetic field as shown in figure 12.7. This is known as the right hand thumb rule. Example 12.1. A current through a horizontal power line flows in east to west direction. What is the direction of magnetic field at a point directly below it and a point directly above it? Solution. The current is in the east-west direction. Applying the right-hand thumb rule, we get that the magnetic field at any point below or above the wire turns clockwise in a plane perpendicular to the wire when viewed from the east end and anti-clockwise when viewed from the west end. In text question 1, draw magnetic field lines around a bar magnet. 2. List the properties of magnetic field lines. 3. Why don't two magnetic field lines intersect each other? 12.2.3 Magnetic field due to a current through a circular loop. We have so far observed the pattern of the magnetic field lines produced around a current carrying straight wire. Suppose this straight wire is bent in the form of a circular loop and a current is passed through it. How would the magnetic field lines look like? We know that the magnetic field produced by a current carrying straight wire depends inversely on the distance from it. Similarly, at every point of a current carrying circular loop. The concentric circles representing the magnetic field around it would become larger and larger as we move away from the wire. Figure 12.8. By the time we reach at the center of the circular loop, the arcs of these big circles would appear as straight lines. Every point on the wire carrying current would give rise to the magnetic field, appearing as straight lines at the center of the loop. By applying the right hand rule, it is easy to check that every section of the wire contributes to the magnetic field lines in the same direction within the loop. We know that magnetic field produced by a current carrying wire at a given point depends directly on the current passing through it. Therefore, if there is a circular coil having n turns, the field produces n times as large as that produced by a single turn. This is because the current in each circular turn has the same direction, and the field due to each turn then just adds up. Activity 12.6. Take a rectangular cardboard having two holes. Insert a circular coil having large number of turns through them. Normal to the plane of the cardboard, connect the ends of the coil in series with a battery, a key, and a rheostat as shown in figure 12.9. Sprinkle iron fillings uniformly on the cardboard. Plug the key. Tap the cardboard gently a few times. Note the pattern of the iron fillings that emerges on the cardboard. 12.2.4 Magnetic field due to a current in a solenoid. A coil of many circular turns of insulated copper wire wrapped closely in the shape of a cylinder is called a solenoid. The pattern of the magnetic field lines around a current carrying solenoid is shown in figure 12.10. Compare the pattern of the field with the magnetic field around a bar magnet, figure 12.4. Do they look similar? Yes, they are similar. In fact, one end of the solenoid behaves as a magnetic north pole while the other behaves as the south pole. The field lines inside the solenoid are in the form of parallel straight lines. This indicates that the magnetic field is the same at all the points inside the solenoid. That is, the field is uniform inside the solenoid. A strong magnetic field produced inside a solenoid can be used to magnetize a piece of magnetic material, like soft iron when placed inside the coil. The magnet is so formed it is known as electromagnet. In text questions, question number 1. Consider a circular loop or wire lying in the plane of a table. Let the current pass through the loop clockwise. Apply the right hand rule to find out the direction of the magnetic field inside and outside the loop. 2. The magnetic field in a given region is uniform. Draw a diagram to represent this. 3. Choose the correct option. The magnetic field inside a long, straight solenoid carrying current is 0. Option B decreases as we move towards its end. C increases as we move towards its end. Or D is the same at all the points. 12.3 Force on a current carrying conductor in a magnetic field. We have learned that an electric current flowing through a conductor produces a magnetic field. The field so produced exerts a force on the magnet placed in the vicinity of the conductor. French scientist André Marie Ampere, born in 1775 and died in 1836, suggested that the magnet must also exert an equal and opposite force on the current carrying conductor. The force due to magnetic field acting on a current carrying conductor can be demonstrated through the following activity. Activity 12.7. Take a small aluminium rod AB of about 5 cm using two connecting wires suspended horizontally from a stand as shown in figure 12.12. Place a strong horseshoe magnet in such a way that the rod lies between the two poles with the magnetic field directed upwards. For this, put the north pole of the magnet vertically below and south pole vertically above the aluminium rod. Connect the aluminium rod in series with a battery, a key, and a rheostat. Now place a current through the aluminium rod from end B to end A. What do you observe? It is observed that the rod is displaced towards the left. You will notice that the rod gets displaced. Reverse the direction of current flowing through the rod and observe the direction of its displacement. It is now towards the right. Why does the rod get displaced? The displacement of the rod in the above activity suggests that a force is exerted on the current carrying aluminum rod when it is placed in a magnetic field. It also suggests that the direction of force is also reversed when the direction of current through the conductor is reversed. Now change the direction of field to vertically downward by interchanging the two poles of the magnet. It is once again observed that the direction of force acting on the current carrying rod gets reversed. It shows that the direction of the force on the conductor depends upon the direction of the current and the direction of the magnetic field. Experiments have shown that the displacement of the rod is largest or the magnitude of the force is the highest when the direction of current is at right angles to the direction of the magnetic field. In such a condition, we can use a simple rule to find the direction of the force on the conductor. In activity 12.7, we considered the direction of the current and that of the magnetic field perpendicular to each other and found that the force is perpendicular to both of them. The three dimensions can be illustrated through a simple rule called Fleming's left hand rule. According to this rule, stretch the thumb, forefinger, and middle finger. Stretch the thumb, forefinger, and middle finger of your left hand as shown to you in figure 12.1 and such that they are mutually perpendicular to each other. So if the first finger points in the direction of the magnetic field and the second finger in the direction of current, then the thumb will point in the direction of motion or the force acting on the conductor. Devices that use current carrying conductors and magnetic fields include electric motor, electric generator, loudspeakers, microphones, and measuring instruments. Example 12.2. An electron enters a magnetic field at right angles to it as shown in figure 12.14. The direction of force acting on the electron will be A to the right, B to the left, C out of the page, and D into the page. Solution answer is option D. The direction of the force is perpendicular to the direction of the magnetic field and the current as given by Fleming's left hand rule. Recall that the direction of current is taken opposite to the direction of motion of electrons. The force is therefore directed into the page. Questions 1. Which of the following property of a proton can change while it moves freely in a magnetic field? There may be more than one correct answer: A. Mass, B. Speed, C. Velocity, and D. Momentum. In text question 2, in activity 12.7, how do we think that the displacement of rod AB will be effective if 1. Current in rod AB is increased, 2. A stronger horseshoe magnet is used, and 3. Length of the rod AB is increased? A positively charged particle, alpha particle, projected towards west is deflected towards north by a magnetic field. The direction of magnetic field is A towards south, B towards east, C is downward, and D is upward. More to know. Magnetism in medicine. An electric current always produces a magnetic field. Even weak ion currents that travel along the nerve cells in our body produce magnetic fields. When we touch something, our nerves carry an electric impulse to the muscles we need to use. This impulse produces a temporary magnetic field. These fields are very weak and are about 1 billionth of the Earth's magnetic field. To maintain organs in the human body where the magnetic field produces significant are the heart and the brain. The magnetic field inside the body forms the basis of obtaining the images of different body parts. This is done using a technique called magnetic resonance imaging, also known as MRI. Analysis of these images helps in medical diagnosis. Magnetism has thus got important uses in medicine. Domestic electric circuits in our homes. We receive supply of electric power through a main supply, also called mains. either supported through overhead electric poles or by underground cables. One of the wires in this supply, usually with red insulation cover, is called the live wire or positive. Another wire with black insulation is called neutral wire or negative. In our country, the potential difference between the two is 220 volts. The students who are watching this live, Dark Whispers, thank you for joining the channel. I have recorded few video series of bio and they are there in the playlist. So complete video series is available for live processes and also word problems of heredity are being taken. So in case you are interested, you can visit the playlist. At the meter board in the house, these wires pass into the electricity meter through a main fuse. Through the main switch, they are connected to the line wires in the house. These wires supply electricity to separate circuits within the house. Often, two separate circuits are used. One of the 15 ampere current rating for appliances with higher power ratings such as geysers, air coolers, etc. The other circuit is of 5 ampere current rating for bulbs, fans, etc. Thank you, Dark Whispers, for subscribing. The earth wire, which has insulation of green color, is usually connected to a metal plate deep in the earth near the house. This is used as a safety measure, especially for those appliances that have a metallic body, for example, electric press, toaster, table fan, refrigerator, etc. The metallic body is connected to the earth wire, which provide a low resistance conducting path for the current. Thus, it ensures that any leakage of current to the metallic body of the appliance keeps its potential to that of the earth, and the user may not get a severe electric shock. Figure 12.15 gives a schematic diagram of one of the common domestic circuits. In each separate circuit, different appliances can be connected across the live and neutral wires. Each appliance has a separate switch to on or off the flow of current through it. In order that each appliance has equal potential difference, they are connected parallel to each other. Electric fuse is an important component of all domestic circuits. We have already studied the principle and working of a fuse in the previous chapter. See section 11.7. A fuse in a circuit prevents damage to the appliances and the circuit due to overloading. Overloading can occur when the live wire and the neutral wire come into direct contact. This occurs when the insulation of the wires is damaged or there is a fault in the appliance. In such a situation, the current in the circuit abruptly increases, and this is known as short circuiting. The use of an electric fuse prevents the electric circuit and the appliance from a possible damage by stopping the flow of unduly high electric current. The joule heating that takes place in the fuse melts it to break the electric circuit. Overloading can also occur due to an accidental hike in the supply voltage. Sometimes overloading is caused by connecting too many appliances to a single socket. In text question 1, name two safety measures commonly used in electric circuits and appliances. 2. An electric oven of 2 kilowatt power rating is operated in a domestic electric circuit 220 volt that has a current rating of 5 ampere. What result do you expect? Explain. What precautions should be taken to avoid the overloading of domestic electric circuits? What do you have learned? A compass needle is a small magnet. Its one end which points towards north is called the North Pole, and the other end which points towards south is called the South Pole. A magnetic field exists in the region surrounding a magnet in which the force of the magnet can be detected. Field lines are used to represent a magnetic field. A field line is a path along which a hypothetical free north pole would tend to move. The direction of the magnetic field at a point is given by the direction that the north pole plays at that point would take. Field lines are shown closer together where the magnetic field is greater. A metallic wire carrying an electric current has associated with it a magnetic field. The field lines about the wire consist of a series of concentric circles whose direction is given by the right hand rule. The pattern of the magnetic field around a conductor due to an electric current flowing through it depends on the shape of the conductor. The magnetic field of a solenoid carrying a current is similar to that of a bar magnet. An electromagnet consists of a core of soft iron wrapped around with a coil of insulated copper wire. A current carrying conductor, when placed in a magnetic field, experiences a force. If the direction of the field and that of the current are mutually perpendicular to each other, then the force acting on the conductor will be perpendicular to both and will be given by Fleming's left hand rule. In our houses, we receive AC electric power of 220 volts with a frequency of 50 hertz. One of the wires in this supply is with red insulation called the live wire. The other one is the black insulation, which is the neutral wire. The potential difference between two is 220 volts. The third is the earth wire that has a green insulation and that is connected to a metallic body deep inside the earth. It is used as a safety measure to ensure that any leakage of current to a metallic body does not give any severe shock to a user. Fuse is the important safety device used for protecting the circuits due to short circuiting or overloading of the circuits. So, with this, we are done with the live reading of Chapter 12 Magnetic Effects of Electric Current. If this was helpful, you can share it with your friends. I have already recorded a video series on life processes and heredity, and complete audiobook is also there for class 10 science students following the NCERT book. In case it was helpful, do consider subscribing. See you in next video. Thank you.